Hey, good afternoon. Welcome back to part 3 of us dealing with a closed system. In which last video we were talking about getting this to being a pure substance of just water, water in the liquid phase and water in the vapor phase. And in the last video we got it both originally to a boiling point to get this to being just water vapor and liquid water, and then we got it back down to being a critical point, so it was all three phases at once. The thing is at those points we know exactly what the pressure and the temperature are. Did I say that right? The temperature and the pressure are at the critical point as well as at the boiling point. So here the critical point and then the boiling point. The thing is though, what do we do when we're anywhere else along the line of equilibrium? And so here we've got this equilibrium between liquid and vapor pressure of the water. And so any other point, what do we do about that? And that's where the relevance of the Antoine equation comes in, is because whenever we change the temperature, the pressure is going to change accordingly. And we want to be able to know what the partial pressure is along any other point, and not just at the boiling point or not just at the critical point, but at any point along that line of equilibrium. And that's what the Antoine equation helps us do and tells us about the pressure, the partial pressure, because the pressure in this system is going to be the partial pressure that is coming from the water vapor, from the water. And so we need to be able to know, because as the temperature changes, so does the partial pressure of the water. And so we want to be able to know the exact partial pressure at any point along this line of equilibrium. And so let's go ahead and start by noting here what the Antoine equation is. Just want to make sure that the whiteboard is up in sight here. Bring this in. Okay, that's not very good. I'll just bring this in right here. So our Antoine equation is going to be log base 10 of our pressure at any point equaling A minus B over C plus T. And so what this means here is that our variables here, T is our independent variable because we can readily change the temperature. And then as the temperature changes, so is our pressure. And it's going to be a log base 10 of the pressure. And A, B, and C are our parameters within the Antoine equation. And so what does this mean when we're talking about all of this? Well, the Antoine equation is let's go ahead and go back to here. The Antoine equation is a semi-empirical theory, meaning that it's partially based on theory that's been confirmed and also partially based on a bunch of experiments that have been tested and conducted in order to know what these A, B, and C parameters are for different chemicals, and in our case, water. So someone has already gone through and experimented with water and tested water and has identified what our A, B, and C parameters are for water at different temperatures and at those corresponding pressures. So let's go ahead, and our next step then will be we're gonna want to try and fit the Antoine equation for data that we collect. We want to be able to fit it both to nonlinear regression and then transform that into linear regression. So that's what we're going to go ahead and go to next. So here we're going to try and fit our Antoine equation and the data we collect to nonlinear regression first. So the way we do that is we need to first go ahead and grab our data for water vapor pressure. And thankfully, somebody has already done the work for us of collecting all of this data and testing water. So we're going to go ahead and find that data real quick. Water vapor pressure. And here it is as an array. So let's go ahead and look at it real quick in the raw form of data. And this is our water vapor pressure. So this first column, this whole array of information here, this first column is dealing with temperature, different temperatures, and then this second column is dealing with pressures. And so what we can do here is we can copy and paste this and drop it right into there. And the really cool thing is it just went and uploaded it for us. And so we can now find it. See if it uploaded it for us. Not seeing it in here. In our files. There it is. Okay, I uploaded it twice because it didn't update. And so now, because we're dealing with an array and a list of values, we're going to go ahead and import numpy. And we don't want to keep typing out numpy every time, so it'll get old. So we'll just go ahead and call it import numpy as np. And now let's go ahead and name our variable. And so in order to name our variable, we need to actually load the text. And what are we loading? Well, we're loading the name of the file here. In this case, it happens to be water vapor pressure.csv. There's two of them that I downloaded, but we'll just take the first one. Now, we need to splice this information because it's in two columns, and we need to be able to separate these. And so what we're going to do here is use a delimiter equaling, and what separates the two columns of information is a comma. So we're going to go ahead and say that's what the delimiter is. Now what we're going to do is see if it actually uploaded properly. Great, look at that. So here we've got our column of temperatures. Here we've got our column of pressures. So that came in nicely. Go ahead and delete that. And so now let's go ahead and label each separately. So our temperature is going to be in the very first column. And trying to find that. Okay, great. And then now our pressure, because remember our Antoine equation is in a log base 10 of the pressure, let's just go ahead and name it log base 10 now, just for tracking that easily. And then we're going to grab that's in the second column. Let's just see if it grabbed it. That looks good. Let's see if it grabbed this. That also looks good. Delete, delete, delete. Okay. Now let's go ahead and plot this and see what that looks like. And so we're going to go ahead and from plotly dot subplots, we want to import make subplots. So it's the tool we're going to grab here. And then just for template purposes to have our plot look dark, we're going to import plotly.io as we don't want to keep typing that out every time, so we'll just call it PO. And then PO.templates, our default type here. Default template is going to be, let's do it as a dark background. Okay, so now we're going to go ahead and start a new line of code for plotting purposes. So let's go ahead and call our plot figure. And the way we do that is make subplots, which we just uploaded. Now, here's the fun part. Now we get to add all of our experimental data. So we're going to go ahead and get a bunch of different data forms. So our independent variable, remember, is temperature. So we're going to set x to t. Our dependent temperature is y. The pressure is dependent directly on, did I say that wrong? I think I meant to say, so the pressure is being dependent on the temperature. So as the temperature changes, so does the pressure. So this is going to be our log base 10 of p. And then a thing to note, we're going to make this in markers, as markers, because whenever we're dealing with experimental data, we want it to show up as markers. And the reason for that is because we want to be able to see how well it fits to a model. And so if it's in markers, we're going to be able to see all the individual experimental data points. And then that way we can kind of see when the model is as a line, how well it actually fits over each of those individual points. So we're going to have the mode as markers. Let's go ahead and name it now. And the name is data. All right, let's see what happens. Okay, great. One thing to note with this, though, is this is not being expressed in a logarithmic fashion. So let's go ahead and change our pressure data to reflect that. Okay, so we need to have all of this re-expressed there. Re-update that. Let's see what this looks like. Okay, that looks better. Now, the next step here is to get it into nonlinear regression. And so what's going on with nonlinear regression is we're trying, when we fit a model to the data in a nonlinear regression, we're wanting to really minimize the sum squared error and that sum squared deviation between the data that we've collected and the model itself. And so let's go ahead and define the sum squared error here. And then because A, B, and C are our parameters from the Antoine equation, we'll go ahead and unpack that now. And what's going to happen when we minimize, because again we're trying to minimize that sum squared error, and so when we go ahead and minimize, what's going to get pumped out is a vector of values. So let's just go ahead and name this V, not varsity or var. I don't know why varsity popped in my head, probably because of just all the exciting things with sports and the Bengals going to Super Bowl. And so now A, B, and C unpacked as V. We're going to need to be able to return our sum squared error. So what is the sum squared error? Well, we have to, what we're doing again, remember, is taking the model, the difference between the model and the data. So let's start with our model divided by C plus T. So that's our Antoine equation, that's our model. And what is the data that we're wanting to find the difference of? Well, the data is the log base 10 of P, the pressure. So the log base 10 of P, there we go, that looks good. Now, just as the name itself implies, we take the sum of the square of the error of that difference between the model and the data. So we're going to start by squaring this. There we go. And now we need to find the sum of this. Because now that we've squared all of it, let's go ahead and add it all up. Put that there. See what happens. Okay, it didn't yell at me, so that's good. So now we're going to need to go ahead and minimize find the minimum of the function here, what that gives us. And before we can do that, I didn't actually import that yet. So let's go ahead and from scipy optimize import minimize. So we're just going to go ahead and import that tool in, allow us to find the minimum. Now, when we're of the function with those parameters A, B, and C. So what we're doing now is whenever we are trying to find this, well, return the minimum of the sum squared error, we have to start with some sort of initial guess. And so trying to minimize the minimum of the sum squared error and an initial guess between A, B, and C. So A is, there we go, not A, but A tends to be around 1, so let's give 1 as our initial value, 1 for B should be good, and then 0 for C. Let's see what happens here. Okay, so it gives us a whole lot of information. It said optimization terminated successfully, so that's good to see. All we really need here, though, is what our minimum function is, or the minimum of the function is for each of the parameters. So this here happens to be A, this is going to be our B, and this is going to be our C. So we only want to snag this, and so let's go ahead and go back in here and just grab that, which is great. So now let's go ahead and unpack this equals, no, sorry, we're going to come up here because we want to unpack it to the actual value of what we found there. So now let's see if it worked. Great. Okay, so it snagged each of the values accordingly, A, B, and C. So now all we have to do is plot our minimum parameters to this and see how well the model fits with the data. So let's go ahead and do that up here. See. Now, y doesn't equal the data anymore. we've done the data, the experimental data is on there. Y now equals the model, which is again the Antoine equation. If I can get that, there we go. And then, there we go. And now because we're dealing with the actual model now, we want to see how well it lines up, so we'll do it as lines to see if it actually goes over our experimental data. And let's call this Antoine equation non-linear. All right, let's see what happens. All right, it didn't like that. Let's see, what did I do wrong? Scatter. Okay. Make subplots. T. Let's put the variable parsing. Oh, I didn't close it out with the parentheses. Okay, this lines up nicely. That's great to see. The only problem is, it's not really a problem, but it's just not as pretty. We don't have our model spaced out evenly, and so we've got chunks like this where it's in a linear fashion. We want it to be more of a curve. So let's go ahead and fix that by setting a new variable, and our new variable, the parameters will be the freezing point of water really, really hot, and 100 points. Now, before we go ahead and run it, we need to change our variable names. Let's see what happens. Okay, it definitely did not like that. That would probably help if I actually gave it something to do here. There we go. Okay, let's try this. That's much better. Okay, so that is our Antoine equation as a nonlinear regression fitted to our experimental data. And so now what we're going to do next is move on to the Antoine equation transformed into a linear regression to then see how well that matches the data. So the way we transform our Antoine equation to enable it for a linear regression, to fit it to a linear regression, is by using design matrix vector multiplication equaling a vector. And so let's go ahead and take a look at what that looks like here. Before we go ahead and code it all out, we have to actually set our equation. So here again is our, there's a glare. Here is our Antoine equation. And what we're dealing with here is we know the data for pressure and for temperature. So temperature is our independent variable and pressure is our dependent variable. And so these are the elements that can go inside our matrix. And then our parameters are going to have to be, they're going to have to get isolated all to one side. The reason they have to get isolated all to one side is because they have to be able to be expressed in the matrix vector multiplication. And so what we'll go ahead and do is isolate our parameters all to one side of the equation. So let's go ahead and multiply this by this side, and then factor this all out. So we have C log 10 of P plus T log 10 of P equals AC plus AT minus B. Then let's go ahead and we're going to need to still isolate all the variables, not the variables, but the parameters on the one side. And then the way we do that is, let's go ahead and express our t-value first for the purposes of the design matrix. And then we're going to want the pressure to come next, and because these are on opposite sides, we have to negate this. So we'll go ahead and negate, sorry, not this one, but this one with the C, because we want the parameters isolated to one side here, log 10 of P. And then we have AC minus B, and then on the other side, we have our data all by itself. So now what happens next is we're going to be able to express this in a design matrix. Our parameters are going to be expressed as a vector, and the result is going to be a vector. So just what's going to happen here is we're going to have our T1, T2, all the way down to Tn in the matrix of our array of values that we found in our experiment. Then we have our negative log 10 of P1, negative log 10 of P2, all the way down to negative log 10 of P. And then we're going to go ahead and be able to put in our A. We have our A, we have our C. We're going to be able to know what A is, we're going to be able to know what C is. We don't know what B is just right off the bat after doing matrix multiplication, but a way we can get around that is if we set this right here to a different named variable. Well, in this case, we'll call it D. Yeah, you can see that. And then, so we'll go ahead and put D down here. And then here, what's going to happen is T1 log 10 of P1, T2 log 10 of P2, all the way down, Tn log 10 of Pn. So we're almost to where we can do matrix multiplication. The one problem right now is we have a 3 by 2, and we're trying to multiply by a 3 by 1, and that will not work with the way that matrix multiplication works. And so what we have to do is make a big long column of ones to multiply by. And then what that's going to allow is we're going to have our 3 by 3 by 3 by 1 that's going to result in our vector. And so let's go ahead and call this 3 by 3 matrix Q. We'll call this B. We'll call this, let's switch that around here. Let's call this V and this B. And then what that means here is we've got QV equals B. Then what we're going to have to do is take the transpose of that. So we transpose our matrix by both sides. And this is the design matrix multiplication equaling a vector that we're going to need to solve and code now for in order to transform our Antoine equation and express it as a linear regression. I should make one last note. Coming back to B, what is B going to equal? Well, we know that D, in this case, equals AC minus B. So just real quick doing some algebra, D minus AC equals minus B, which means that B equals AC minus D. So that's going to come into play as well to find all three parameters for the Antoine equation. So now, I'm going to go ahead and pull up our code here. So this is where we left off, and this was from our nonlinear regression. Let's go ahead and get to the next point here and set up our matrix. So our matrix we called Q, and then we're going ahead and set up, so np.c, we're going to end up joining our matrices together here. So we've got T as our first set of values that we found, log, not log, but negative log 10 of P, because that was what we had set up in our equation for the matrix. And then now here's how we get our big column of ones. In order to make it a 3 by 3 matrix, we do np ones underscore like, and we'll make it like T because it'll be just as long that way. And let's go ahead and see if it worked, which it looks like it did. Great. Go ahead and delete that. And so now we're going to go ahead and get our parameters set here. The reason I'm typing in A2 and C2 and D2 is because we've already named A, B, and C earlier in this list of code for our nonlinear regression. So now we'll go ahead and do A2, C2, and D2 and solve that. So lin alg solve. And what we're solving here is what we just worked out on the whiteboard, which is our matrix multiplication. So Q transposed multiplied by the matrix, 3 by 3 matrix, and then Q transposed multiplied by the other side of the equation, which was our array of vectors, which in this case happened to be T, the temperature, times log 10 of P, the other side of the equation. Didn't like that. What is our problem? Our array, numpy array, is not callable. Okay. There it is. I forgot to mark that it needs to be. There we go. Forgot to mark that it needs to be matrix multiplication with the transpose. Okay, so now let's go ahead and set our B, which again, we already worked that out, also on the whiteboard, is A2 times C2 minus D2. Now let's go ahead and see if it all actually worked out. That looks great. That looks very similar to the values we had for the minimum function for our parameters from the nonlinear regression. So let's go ahead, and the last thing we'll do here is graph this. And we'll have it evenly spaced though, so we'll use tplot. Now our model is our variables that we just found. And then mode equals lines, again, because we're dealing with the model, the linear regression model, so we want to have it expressed as a line. This one we'll name differently, if I can get my equals, Antoine equation linear. And let's see what happens. If it, look at that. That is great. So we have a very close fit of the data lining up, and that is great to see. That is what we were hoping for. So that is how we transform the Antoine equation through design multiplication of a vector equaling a vector in order to enable it to be used as a linear regression. And again, in this video, we talked about the relevance of the Antoine equation, so we can know the pressure, the exact pressure at any point along that equilibrium line between liquid and vapor. And then we modeled it and fitted it from experimental data with the Antoine equation model, both as a nonlinear regression and as a linear regression. Thank you.